everyone! Welcome back to my channel, Trash to Teach.
Build a fully encrypted Raspberry Pi comm server, no subscriptions, no cloud. This is a fully encrypted messaging server, no monthly fee, no company sitting between you and your messages, and it's running on a $50 Raspberry Pi sitting right here on my desk. By the end of this video, you'll have the exact same thing running on your own hardware, encrypted at rest, encrypted in transit, and completely under your control. No cloud subscription, no third party, no monthly bill. Let's build it. Why this matters. Before we touch any hardware, let's talk about why you'd even want this. Every major messaging platform, even the ones that advertise encryption, still runs through servers you don't control. Metadata, timestamps, who talked to who, account information. A lot of that lives on someone else's infrastructure, governed by someone else's terms of service, which can change anytime they want. Self-hosting flips that. When you run your own server, you decide where your data lives, who can access the machine, and how long anything is retained. There's no company to subpoena, no server outage on their end taking down your access, and no surprise price increase because they added a premium tier. That said, I want to be upfront about the trade-offs because self-hosting isn't magic. You are now responsible for keeping the server updated and secure. If you ignore security patches, you're worse off than using a maintained commercial service. Your uptime depends on your home internet and power staying on. This isn't a redundant data center. And if you lose your Pi's SD card without a backup, you lose your data, so we'll cover backups too. If you're fine with those trade-offs in exchange for full control and zero subscription cost, this build is for you. Here's exactly what you'll need before we start. A Raspberry Pi 4 or Raspberry Pi 5 4 GB of RAM minimum, 8 GB if you want headroom. A micro SD card, 32 GB or larger, ideally a good quality one. I'll link the one I use in the description and pinned comment. A reliable power supply, the official Raspberry Pi power adapter, not a random phone charger, because underpowering is the #1 cause of weird, hard-to-diagnose Pi problems. An Ethernet cable is optional but recommended for the initial setup. It's just more stable than Wi-Fi while we're configuring things. And on the software side, everything we install today is completely free and open source. Raspberry Pi Imager, Raspberry Pi OS Lite, and a self-hosted messaging stack, zero cost, start to finish. Part 1. Flashing the OS. Step 1. Get the operating system onto the SD card. We're using Raspberry Pi OS Lite. Lite just means no desktop environment. Since this is a server, we don't need a graphical interface, and skipping it saves resources for the actual server workload. Download Raspberry Pi Imager from the official Raspberry Pi website. Links in the description. Always grab it from the source, never a random mirror. Open it up. Under Choose Device, select your Pi model. Under Choose OS, go to Raspberry Pi OS Other and pick Raspberry Pi OS Lite, 64-bit. Now, before you hit click the gear icon or the settings option in the bottom right. This is the important part because it lets us pre-configure everything so we never need a monitor or keyboard plugged into the Pi at all. That's called a headless setup. In here, set a host name. I'm using comm server, but name it whatever you'll remember. Enable SSH and choose Use Password Authentication. For now, we're going to lock this down further in a few minutes, so don't worry about it being temporary. Set a username and a strong password. Do not leave this as the default Pi username with a weak password. That combination is the first thing any scanner on the internet tries. Configure your Wi-Fi if you're not using Ethernet, and set your correct country code. This matters for Wi-Fi regulatory compliance. Save those settings, insert your SD card, select it as the target, and hit write. While that's writing, quick note. This process fully erases the SD card, so make sure you've selected the correct drive before confirming. Writing usually takes 5 to 10 minutes, depending on your card speed. Once it's done, eject the card, pop it into the Pi, connect Ethernet if you're using it, and power it on. Give it about 60 seconds to boot for the first time. Part 2. First connection and hardening. Now we connect over SSH from our main computer. Open a terminal. On Windows, that's PowerShell. On Mac or Linux, it's just terminal. And type SSH username at comserver.local. If that hostname doesn't resolve on your network, you can instead find the Pi's IP address through your router's device list and connect with SSH username at its IP address. You're in. First thing, always update the system. This pulls the latest security patches. Reboot when it finishes, then SSH back in. Now let's harden this box before we install anything else, because an unhardened server exposed to the internet is a bad time waiting to happen. Step 1. Change the default password if you haven't already, using the password command. Step 2. Set up key-based SSH authentication so we can eventually turn password login off entirely. On your own computer, not the Pi, generate a key pair if you don't already have one. That copies your public key to the Pi. Test it, open a new terminal window and SSH in again. If it connects without asking for a password, the key is working. Now back on the Pi, we disable password login entirely so only your key can get in. Set password authentication to no and permit root login to no. Nobody should be logging in directly as root. Save the file, exit, and restart SSH. One more hardening step of basic firewall. We only want to allow SSH and the ports our server actually needs, nothing else. That opens SSH and HTTPS traffic only and blocks everything else by default. This alone stops the vast majority of automated scanning attacks that hit random ports. With hardening done, we're ready to install the actual comm server. Part 3. Installing the self-hosted comm server. For the messaging server itself, we're using a lightweight self-hosted stack. This keeps things simple enough to run comfortably on a Pi while still giving you real end-to-end encrypted messaging between your own devices. We'll install Docker first, since running the server in a container keeps our Pi's base system clean and makes updates and backups much simpler. That last command lets you run Docker without typing sudo every time. Log out and back in for it to take effect. Now let's create a working directory and a Docker Compose file. This file describes everything our server needs to run in one place. I'm walking through this line by line so you actually understand what's happening. Not just copy-pasting blind, we define the service, tell it which image to pull, map the ports it needs, and mount a local folder for persistent data that's important, because without that mount, all your data disappears the moment the container restarts. We also set environment variables here for the server name and the admin account, and critically for enabling encryption on the database and file storage. That -D runs it in the background, and the logs command lets us watch it start up and confirm there are no errors. Give it a minute or two on first run, it's initializing its database. Common errors and fixes. Now, a few errors people commonly hit right here so you're not stuck if you see them. Error 1. Port already in use. This means something else on your Pi is already using that port. Fix it by checking what's running with sudo lsoff-i:443, stopping that service, or changing the port in your compose file. Error 2. The container keeps restarting in a loop. Almost always a typo in the compose file. Check your indentation. YAML is picky about spacing, and a single misplaced space will break it. Error 3. Permission denied on the mounted data folder. Fix it by making sure the folder ownership matches the user ID the container expects, usually solved with a sudo chown-r command on that directory. Part 4. The encryption layer. Having a self-hosted server is step 1. Making sure it's actually encrypted both while data moves and while it sits on disk is what makes this meaningfully private, instead of just not big tech but still wide open. We need 2 layers here, encryption in transit, meaning the connection between your devices and the server, and encryption at rest, meaning the data sitting on the Pi's storage. Having a self-hosted server is step 1. Making sure it's actually encrypted both while data moves and while it sits on disk is what makes this meaningfully private, instead of just not big tech but still wide open. We need 2 layers here, Encryption in transit, meaning the connection between your devices and the server, and encryption at rest, meaning the data sitting on the Pi's storage. For encryption in transit, we need a TLS certificate, so all traffic to the server is HTTPS, not plain HTTP. We'll use Caddy as a reverse proxy. It automatically requests and renews free TLS certificates for us, so we don't have to manage that manually. Then we point Caddy at our domain. If you don't have your own domain, you can use a free dynamic DNS service. I'll link one in the description since a domain name is required for automatic HTTPS certificates to work. Save that, restart Caddy, and it automatically requests a valid certificate and starts forcing everything through HTTPS. Verifying encryption is actually working. And here's the part most tutorials skip, actually verifying it, instead of just claiming it works. We'll check this two ways. First, in a browser, navigate to your domain and look for the padlock icon, click it, view the certificate, confirm it's valid and issued to your domain. Second, and this is the more rigorous check, we use a command line tool called OpenSSL to inspect the actual handshake. If you see verify return code 0, OK, and the protocol listed as TLS 1.3, your connection is genuinely encrypted with a modern, secure protocol, not just claiming to be. Encryption at rest. Now for data at rest, the messages and files actually stored on the Pi's SD card. Most self-hosted messaging stacks support database-level encryption through an environment variable we set in the compose file earlier. But we're going to go a layer further and encrypt the entire data directory using LUKS Linux's built-in disk encryption, so that even if someone physically stole this Pi, the storage would be unreadable without the passphrase. This creates a 4 GB encrypted container, formats it, and we mount that as the data directory Docker writes to. Adjust that size for how much storage you actually need. One important trade-off to be honest about, because this container needs to be manually unlocked with a passphrase, your server won't auto-start its encrypted storage after a power loss without you SSH-ing in and unlocking it. That's the security versus convenience trade-off of at-rest encryption on a headless device. Some people are fine leaving the key on the device for full automation. I'd recommend against that if privacy is the whole point of this build. Part 5. Connecting a client and sending a real message servers up, encrypted in transit and at rest. Now let's actually use it. Download the client app that matches your server stack links in the description for iOS, Android, and desktop. Open it, and instead of signing into someone else's server, choose Custom Server or Self-Hosted, and enter your domain. Create your account. Remember, this account only exists on your server, in your database, encrypted at rest, on hardware sitting in your house. Let's send a real message between two devices and confirm it actually works end-to-end, and there it is, a real encrypted message sent and received, with the entire round trip happening on infrastructure you fully control. No subscription, no third-party company in the middle. Part 6. Backups. Don't skip this. Before we wrap up, I need to cover backups because I've seen too many self-hosting videos skip this, and self-hosting without backups just means you've replaced my data is on someone else's server with my data is on one SD card with no backup. That's not actually safer. The good news, because we containerized everything with Docker and kept our data in a defined volume, backups are simple. This stops the server briefly, compresses the entire data directory into a single dated archive file, then brings the server back up. Copy that archive off the Pi to an external drive, a NAS if you have one, or an encrypted USB stick. I do not recommend uploading it to a cloud drive unless it's already encrypted, because that would undercut the entire point of this build. You can automate this with a simple cron job so it runs weekly without you thinking about it. That line runs the backup automatically every Sunday at 3 a.m. Set it, forget it, and you're covered if the SD card ever fails, which on Pi projects eventually happens to almost everyone. Recap and wrap up. We flashed a headless Raspberry Pi OS install with SSH pre-configured. We hardened it, key-based login only, no root SSH, and a firewall allowing only the traffic we actually need. We installed a self-hosted messaging server in Docker for clean portable deployment. We layered on real encryption, TLS in transit through an automatic HTTPS reverse proxy, and LUKS encryption at rest for the actual stored data, and we verified both instead of just taking it on faith. We connected real client apps and sent an actual encrypted message end-to-end, and we set up automated backups so a single SD card failure doesn't mean losing everything. All of that on a $50 computer using entirely free and open-source software. No subscription, ever. If you want to keep building out your privacy-first home setup, I've got 2 related videos, one on running a completely offline local AI assistant, and one on building a hardened VM sandbox for safely testing untrusted files. Links and playlist right on screen now. Drop a comment with what you end up hosting on your Pi. I read everyone. Subscribe if this was useful, and I'll see you in the next build.